Hello forensic science classes, we are continuing Unit 11 on serology and blood spatter, and this video is going to be on the blood spatter portion. So one of the first things we have to talk about is how it is in fact blood spatter and not blood splatter. Sometimes you'll even hear people on the internet incorrectly calling it splatter, but there's no L. The correct term is spatter, and essentially what it is we're analyzing how to reconstruct the crime scene based on how the blood sprayed. And there's all kinds of different things that we can tell just by looking at the way blood hit a surface. Some of the things include maybe the type of weapon that was used, the location of the original injury, the velocity or force of the impact, the path the victim took or the suspect if the blood was traveling, and there's all kinds of other things that we'll be looking at in this video and in this unit. First we have to get some of the vocab out of the way. So one of the things we're going to be talking about is the parent drop. So the parent drops are sort of like the initial drops. Now this is all happening very quickly, but as the initial drops strike the surface, those first drops are the parent drops. From there are other drops that could be essentially breaking off from the parent drop. So one example is something called a satellite. A satellite is specifically the blood that breaks off completely from the parent drop. So completely separate droplets. You see an example over here. This would have broken off from this parent drop here. And then we also have spines, which are different in the sense that they are like sort of attempting to break off, but they're still connected to the parent drop. And another thing that we have is something called tails. So tails are produced as a result of blood becoming elongated in its forward motion as some blood sticks to the surface while other blood sticks to the remainder of the blood. Cohesion. So that's sort of what's causing all this, is that sort of like when you work with water where water forms droplets, blood does the same thing because of cohesion. So blood's very good at sticking to itself, and it takes additional force essentially to get blood to break off from other blood, and that's going to give us some clues. So in order to cause satellites to happen or spines to happen or these elongated tails, there's going to have to be essentially significantly more force from that blood in order to get it to break off from the other blood, and that's going to give us some clues. And here's our elongated tails here, so we can sort of tell that actually this blood was going down and to the right because of the way the tails are, which we'll talk about in a second. So one of the things we can tell from all of these that we just mentioned is the direction the blood was traveling. So for example, this blood was traveling to the right because those satellites, see how these are disconnected, are leading to the right. So those spines, those satellites, and those tails lead the direction in which the blood was going. They lead in front of the blood. So this person must have been traveling to the right while they were bleeding essentially in order for this to happen. So all of those are going to lead in front of the parent drop to tell you the direction of the blood. Now what's also important is if blood happens to drop straight down, so let's say it had no motion except for it just drops straight down onto the floor or onto the surface, then it's going to kind of have equal spread of spines and at the same time these satellites, and essentially they're not going to be leaning more to one direction. When blood has directionality, there's going to be more of an emphasis on spines to one side. So maybe if the person was going to the left, we would see more satellites or more spines to the left, or just only satellites and spines on the left side. But if blood was dropped straight down without much motion to it, then we're going to see sort of equal distribution of spines and satellites going around the blood. Speaking of blood dropping straight down, one of the things that we can tell about blood, especially the blood dropping straight down, is we can get some clues about the height from which it was dropped. So the pattern that we're looking at is that the higher the blood droplet was dropped from, the wider the diameter of the droplet that forms. And that again goes back to our talk about cohesion. So if blood is dropped from a relatively lower height, let's say 6 inches, then it's not going to be collecting that much acceleration from gravity. And then so when it hits the ground, it's going to exert much less force to try to sort of separate that cohesion. So when blood smashes into the ground from a lower height, it's not going to be smashing and then trying to spread out as much, versus blood that's dropped from as high as 7 feet. That acceleration gain is going to cause it to be more likely to put some more force on that cohesion where the blood sticks to itself and cause it to spread more, and also cause, if you notice the pattern here, we have relatively pretty much no satellites in this portion, whereas as we get further and further distance from the ground, not only does the blood get wider in diameter, the drops, but also we see some more satellites forming, and the satellites are further away as well. So essentially the larger the drop, the larger the distance that it must have come from relative to other drops. Let's take a look at what happens if blood drops into other blood.
My name is Steve Schlebe, and I'm a criminalist with a local law enforcement agency. Oftentimes it seems we will see blood dropping into blood. To demonstrate what it looks like when we have blood dropping into blood, we'll do that on a board like this. First one onto the board, followed by several others. Blood drops into blood, and the subsequent secondary or satellite kind of droplets occur as a result of that, not only on, say, a flat surface around the blood pool where blood is dropping into blood, say on the floor, but on vertical surfaces that might be nearby that will get small droplets deposited on that vertical.
So now what we're looking at is the angle of impact with the blood. So we'll start with the blood that we were just talking about, where if blood drops straight down. So what we're saying is that if we have our surface here, here's our flat surface, a 90-degree angle of impact will be the blood just dropping straight on, completely perpendicular to the surface, just dropping straight down. And we know that that's going to be looking about the same all the way around, right? We're going to have equal spines all the way around, equal satellites if possible all the way around, and there's not going to be any directionality given to that blood. This is what it's going to look more like if we have a 70-degree drop. So compared to the surface, here's our flat surface. Instead of dropping straight down, it's dropping at a 70-degree angle of impact. And we notice that we see more prominent side, the spines begin to become more prominent on the side of the spatter opposite the angle. So like we said, kind of gives us a little bit more directionality, but we'll start to see more spines to one side as we get this angle changing. And then as this angle gets smaller again, it starts to become gradually more and more emphasized, and we start to see the blood droplet become more sort of elongated as we go lower and lower in angle of impact. So notice how here's our flat surface, we're getting closer and closer in angle to the point where, like we said, if 90 degrees had been perfectly perpendicular, 0 degrees is no angle of difference. As our angle gets smaller and smaller, we're actually seeing more elongated blood. So let's look at 45. And in this case, we're starting to see, again, more and more of the spines happening, the blood's elongated, and then if we look at 25, then we have full-on tails, right? So the pattern we want to be aware of is that the blood's becoming more and more elongated as a result of this decreased angle. So the greater the angle, the less the elongation of the blood, and the lower the angle, the more elongated the blood droplets become. So here's sort of a summary of the visual that we were just looking at, where again, if blood is dropped straight on, it's going to have spines on all sides and perhaps satellites on all sides. And then as you get smaller and smaller in angle, we see the blood becomes more elongated as a result. Here's our cartoon image, but then here's our more realistic image. And so like we said, the smaller the angle between the surface and the source of the blood, the more elongated the blood is. And this matters. How can we use this? Well, we can actually take the blood droplets and measure the length and the width, and we can apply a mathematical equation that will actually allow us to determine the angle from which the blood struck the surface. So again, we're trying to reconstruct the scene and figure out where was that person being attacked from, how high off the ground were they, or from what angle did this hit the wall from. We're trying to get an exact location exactly of where this took place so that we can put it all together and reconstruct the scene. So now we're going to take a look at the velocity of the blood. So how do we tell the velocity of the blood based on looking at it? So in general, here's our examples of low, medium, high velocity. So we would have low velocity blood from maybe like a simple drop, or typically from blunt force trauma, so maybe somebody struck with a baseball bat. Medium velocity comes from more violent beating or stabbing, essentially. So the cast off from the stabbing we could see, which we'll talk about in a little bit. And then gunshot wounds are more likely to give us the high velocity, actually. So that's when you see more of a spray. So what is all this? How can we use this to figure this out? Well, in general, the lower the velocity, the larger the size of the droplets. So we're finding that as the blood is moving slower, the droplets are not that much. Essentially, they're all much larger. And then if we have medium, maybe moving 25 feet per second, then we're seeing that the droplets are getting smaller. And then if you have a high velocity, so 100 feet per second, we're seeing that's less than 1 millimeter per droplet essentially. So if we look back at our image, we can see that this would be more from like we said, a gunshot wound. And literally the droplets are so small here that it looks almost like a haze. So it looks more like almost like a uniform haze that we're seeing, because those droplets are just so small that it looks almost like a fog of blood. Whereas the low velocity are more defined, and they're also larger droplets. So the higher the velocity, the smaller the droplets, and the lower the velocity, the larger the droplets, essentially is what we're saying. So now we're looking at an example of something called transfer patterns. So there's two of these we're looking at. One of them is called a wipe. And a wipe is different in the sense that it's smearing blood that already existed on a surface. So there was already blood on that table, somebody ran their hands through it, and that is a wipe. They're almost as though you were trying to wipe it up and failed, sort of. Something that's different but confusingly similar is called a swipe. A swipe is when there was actually no blood on the surface, but there's instead blood on your hand or the object that you're using, and now you wiped blood onto the surface. And so the big difference, you can't always tell looking at it, to be honest, but one of the ways to tell is, for example, in this picture of this wipe, you can see that the blood already started to sort of stain drops where it was originally placed, and then somebody wiped through it, essentially. Whereas the swipe, we don't see any evidence of there originally being a blood pool. It just looks like someone bumped up against the surface with the blood they already have on them. So again, a wipe is essentially blood was already there, wiped through it on the surface, and a swipe is when there was no blood there before on the surface. So let's take a look at kind of more detail what that looks like.
Swipes and wipes are terms that are used to describe ways in which blood is put onto a surface. Wipe occurs when something that is not blood-stained wipes through an already existing blood stain. A swipe occurs when a bloody object being moved along and across an unbloody surface.
And our last one we're looking at is something called the cast-off pattern. So a blood-stained pattern created when blood is released or thrown from a blood-bearing object in motion. So if somebody is beating somebody with a weapon, and they're doing it several times, oftentimes the blood will be cast off from that object while it's being swung. And so how do you tell that? Well, you can tell because the blood tends to go in a relatively confined straight line. It's not kind of spread far and wide. It just happens in a straight line. And sometimes it can also give you clues about the weapon that was used. So for example, a pipe is going to give more, maybe these wider droplets, whereas a pool cue might give you smaller droplets. But either way, we're seeing a straight line where, again, the blood is being cast off, it's being fired off from that weapon while the weapon's being swung. And usually more than one time the weapon's being swung. So let's take a look at that.
With cast-off stains, we're dealing with a situation where there's blood on an object, and that object is being swung through space, and the blood is flying off of that object, striking walls, people, floors, whatever happened to be in the way. You can see in cast-off stains, the stains tend to appear in linear patterns as a result of the arcing strike, in this case with the crowbar.
So now that we've looked at all these, now it's your job to test yourself. There's a Google form, and you want to test yourself to see what you can tell from the blood spatter that's being shown there.